Pambuccian. Please, Victor, you have the floor.
Can I make this small now or not?
Yes, yes.
Okay, good. So today's lecture is about work that is by others. This is my contribution, is tiny and it comes in the end. So, and there's a downside to it, namely the lecture on intuitionism itself will come afterwards. So we'll have to wait a bit until we see what the underlying reasons are. So we're going to go into it as if we knew something about intuition. It's more just focus on the purely formal aspects of it. So I'll start with the history of incidence geometric axiomatizations. And first of all, it's unusual that there is at all a tradition of intuitionistic axiomatization of geometry, because you would think, well, why would Brouwer or anyone who, thinks intuitionism is worth pursuing be interested in axiomatization? Isn't this the formalist's game? Why would an intuitionist do that? Well, this is a rather narrow view. Actually, Brouwer himself was very well read in axiomatic geometry. In fact, he had read everything that was written in the beginning of the century and the end of the last century intensely. And he held a course on the axiomatics of geometry, completely classical, throughout his career. In fact, his last PhD student was a thesis on classical axiomatization of projective geometry. So what is the view then of axiomatization? It's clearly a different one than in the formal way, where axioms conjure up a world, right? They go like, in the beginning was the word. You tell me something, and a universe springs up of that. You have this demiurgal power to create things. That's not the way intuitionism sees it. Intuitionism believes that you have already constructed in your mind some structure, and the axiomatization is telling you what are the fundamental things of that structure from which you can understand how it functions. And in fact, Brouwer himself advised his second doctoral student, Adam Heiting, to write a dissertation precisely on this, on the intuitionistic axiomatization of projective geometry. So Heiting himself will in turn teach classical axiomatic geometry and even write a book on the subject, Axiomatic Projective Geometry, which is completely classical. Okay? And by the way, recently a paper appeared in the Transactions of the American Mathematical Society by a bunch of Chinese mathematicians, where they prove for the length of 4 pages, they think there are special Pascal configurations, which are true in all Desargues projective planes, and the proof is in Heiting's book in 3 lines. I mean, all the results of this paper were known, but if you publish things and speak about functions and the things that are cool in mainstream mathematics, then that gets published. So, what is the problem with intuitionistic projective geometry? Well, the essential complication comes from the fact that you don't know if very close points where you can't define how close they are, where you can't say their distance or their apartness is greater than something known, how will you join them with a line? How would you intersect lines that are very close to each other? That kind of stuff. So in this sense, the concerns of intuitionists mirror the concerns of Barbillian, Yelenslev, or Klingenberg geometries, where we talked about them in the first lecture, and they have this nearness predicate, where if the points are very near, then you can't do the unique things that you liked. So this remoteness notion is called apartness. In the first works by Heiting, it was denoted by little omega. Later on, it got this sign, apartness. What are the main properties of it? Well, if you know that A is apart from B, A and B being points, then for all C, one of C is apart from A or C is apart from B must hold. Also, you have that if it is contradictory that A is apart from B, then A is equal to B. This doesn't mean that it works the other way around, as things are in intuitionism. So, based on this apartness, you can introduce remoteness notions between a point and a line by saying that P lies outside L, meaning that for any points Q that are on L, P is apart from Q. So in his thesis in 1925, which was written in Dutch, Heiting assumed both order and continuity. These were completely abandoned in his long paper in the Mathematische Annahmen in 1927, where he used only incidence and these apartness notions. And his axioms were modeled after Pierre's axioms. So he did whatever you need to do to make them meaningful intuitionistic. Heiting's axiomatization was a three-dimensional projective geometry. And what he showed is how to introduce coordinates, how to prove Desargues' theorem, showed the connection between Pappus and the commutativity of the skew field that you can construct with Desargues. He showed a form of the fundamental theorem of projective geometry. So the idea was to show that you can recover classical projective geometry in the intuitionistic setting without losing anything. I mean, you do more work, but you get the same thing. In other words, intuitionistic mathematics is not mutilating classical geometry. That's kind of the idea, because at the time, it wasn't clear how far you could rebuild mathematics on an intuitionistic basis. And this was an example that, well, you can go that far. The next page in this intuitionistic axiomatization of geometries came in 1949, so rather late. And meanwhile, in 1930, Heiting had formalized intuitionistic logic. Why did he do that? Well, because there were disputes about, the strength of this and that, and everybody had formalized their own things. I mean, logicists and formalists. And so the question was, how do you enter into a debate with these people if you use only words of natural language and don't speak their language. So the idea was to speak their language so you can debate them on their own turf, which is what Heiting did in 1930. Brouwer himself was highly pleased with Heiting's work. However, as related by Heiting, Brouwer always maintained that formalization is unproductive, a sterile exercise. He never changed his mind about that. In other words, not everything that you can express in intuitionistic logic is meaningful, and vice versa. Brouwer could imagine mathematical truths that can never be written down in any language. So more about this when we get to the intuitionist lecture. There was a Franois there that rolled and disappeared. Yeah. Anyway. In the meantime, Griss, who was both a mathematician, he got his PhD with a colleague of Brouwer's, Heisenberg, and he wrote on philosophy a lot, published a series between 44 and 51, a series of articles on negationless intuitionistic mathematics. His idea was that since every mathematical concept originates in a construction, what does a negative thing mean? It means that I cannot perform that construction. Well, that means that the notion itself is meaningless. So he suggested there should be a possibility to reconstruct intuitionistic mathematics on a negationless basis. So what happened to that? In 1948, Brouwer read these things. Griss was his student, but his undergraduate student. He didn't do his PhD with Brouwer. And he showed that there are essentially negative properties by displaying a certain sequence of rational numbers for which it can be shown that it is convergent. But the thing it is convergent to is not zero, yet it is neither positive nor negative. So in other words, this is an essentially negative property, right, that you have. So you can't remove the no. You can't remove it's not true that the limit is zero by saying that the limit is something positive. Because those positive things are contradictory. You can't say them. So that his mathematics contains such things, so you can't get rid of the negation sign, of the fact that all you can say that something is not zero, you can't say something positive about it. At any rate, Nicole de Croix produced an intuitionist axiomatization without negation of projective geometry. First, she wrote two-page articles in the Compte Rendu de l'Académie des Sciences Paris in 49 and 50, and then she wrote the booklet in 55 that contains the extended, how you do it. As happens often with things in intuitionistic axiomatization, this wasn't followed by anything. So it was an island in the ocean. But when Nicole de Croix started publishing her negationless axiomatization of projective geometry, which Hans Freudenthal praised as the système hors élégant, there was no formalization of negationless intuitionistic mathematics. So she did whatever she thought that you should do in a negationless setting. Such formalizations appeared later, between 53 and 2000. And Those of Nelson and the Krivtsov contain only existential quantification and a special implication sign, but no disjunction symbol. Decoy frequently uses disjunction. So the question is, how do you do this if you were to stay with Krivtsov, say, or with Nelson, or no? It's not known because nobody followed up on that. Between December 24th and January 2nd, between 57 and 58, Tarski organized in Berkeley a conference bringing together everybody who did whatever in the axiomatics of geometry and physics. A Romanian mathematician, Alexandru Froda, was invited as well, but couldn't attend for obvious reasons because of the wrong year and the wrong country. So at this conference, Heiting, it was published as the Axiomatic Method in 1959 by Holland. And Heiting came back to the intuitionistic axiomatization of geometry. And this time, his question was, how do you extend an intuitionistically axiomatized affine plane to its projective closure? And this turns out to be incredibly hard in intuition. Dirk van Dalen, who was Heiting's doctoral student, took up the subject and showed that 3 of Heiting's axioms were superfluous, and succeeded in providing a very elegant extension of affine planes to projective planes. He also looked at the connection between order in the affine plane and order in the projective plane, that's hopeless, and order in the underlying algebraic structure, which is a skew field, which is a ternary field. How do you extend that to what's the connection between the order there and the order there? That's also complicated. I mean, everything you think is simple in classical becomes elaborate here. In Heiting's 1927, the Mathematische Annalen axiom system, the individual variables are point and lines, and there is point apartness and point line incidence as primitive notions. In 1996, Van Dalen shows that you can get rid of this many things. I mean, you don't need both point apartness and point line incidence. You can get by with just one apartness relation, the relation of point being distant from a line. So with this, you can get all of your intuitionistic projective geometry. These kinds of preoccupations were very common in classical axiomatizations. Like somebody had several notions and then you're asking, can I do it with fewer? With just one? Pierre, for example, was the first one who did serious work in this line. So here we see a work in intuitionistic axiomatization that does the same, that you can simplify the language. The next to show up in the projective geometric, the intuitionistic axiomatization of projective geometry is Mark Mandelkern, who is retired for a long time, he's 80-something, and lives in New Mexico somewhere in a place which is functioning only with solar. So he used to be a professor at the New Mexico State University in Las Cruces. So in 2007, he offered a Bishop-style constructive algebraization of the Zardian affine planes. Why? He is a disciple of Eric Bishop. Eric Bishop wrote in 1967 or so a manifesto that how mathematics should be reconstructed on some constructive basis, but without the strictness of intuitionism, without a formal system. So he works all the time on, how you feel that things should be done. So it's not, unless you are Michael Beeson, who wrote the whole book on, the varieties of constructive mathematics, and then he probably can say what is acceptable in Bishop style and what is not. But there is no, to my knowledge, formalized way of looking at it. In a certain sense, it's more allowing of things. In another sense, it's more restrictive. You can't have things like, the creative subject that exists in intuitionism isn't allowed in Bishop's world. So he looked at Bishop-style constructive foundations for affine and projective geometry. In 2006 and 2019, the 2019 paper is a correction of things from the 2016 paper. He provided an in-depth intuitionistic development, not only of plane projective geometry, because we know that Heiting had done that, but Heiting didn't tell us anything about the usual things you're interested in classical projective geometry. What are these usual things? Well, first of all, it's the theory of conics, right? I mean, Steiner and von Stout were interested in just that. That was the bread and butter of projective geometry. Well, you don't see any of that in Heiting. What about poles and polars and all that, which is connected with the theory of conics? There's none of that. Well, Mandelkern provides in 2016 and 2019 a complete development of projective geometry with these things, and it is intuitionistic this time. So the language is two-sorted with points and lines as individuals, and you have two apartness relations, one for points and one for lines, and you have point-line incidence. There are axioms for apartness, 7 of them, Franois axiom and Desargues axiom, and several more that ask for enough elements, such as there exist at least 8 distinct points lying on any given line, and it's dual, through any point there passed at least 8 distinct lines. So these are the kinds of things that you have to do in an intuitionistic setting. In a classical one, you can ask for 3 and it's enough. Well, he couldn't do it with less than 8. It's not clear whether you can get 5 or less than 8. Now, if we move from this projective affine setting, then the first paper in doing anything with a more metric geometry is by Jan van Plato in 1995, where he axiomatized a very weak theory of orthogonality in Martin Löff's constructive type theory. So this is an intuitionistic setup. Well, I'm not going to go into the details of what it is. And it was in 1998, he also provided quantifier-free intuitionistic axiomatization of ordered affine geometry with lots and lots of relation and operation symbols. In 1998, there was a paper by Lombard and Velsey. Sorry, I switched here to consonants. It's Velsey, not the way it's written. They did this with a sextenary predicate, dist, where dist of A, B, C, D, E, F means that AB plus CD, the length of these two segments, is greater than the segment EF. Obviously greater in the intuitionistic sense, that you can find something, 1/2 to the n at least, that is where this is bigger than that by at least as much. When the axioms are interpreted, so they provide an axiom system in terms of this disk for all of, Euclidean geometry. When you interpret them in the axioms, what do you interpret? The quantifiers and the connectors. I mean, and or are common in intuitionistic and classical logic, but they follow different rules. In other words, they mean different things. So if you take the axioms and interpret them intuitionistically, they axiomatize in intuitionistic logic a certain theory, which is strictly weaker than the classical theory which you get by interpreting all those logical signs in a classical way. And the classical theory is equivalent to Tarski's geometry, the one with the elementary continuity axis. So the one that gives you geometry over real closed fields. Now, here comes the greatest advance in this area, which comes from Michael Beeson, who is, I think, the only one who published in both logic and mainstream mathematics, things like differential geometry. In 2010, the proceedings of a conference in Japan, the 10th Asian Conference on Logic or something like this, were published, in which Michael Beeson started a sequence of papers that will lead to a really important paper in 2018. So the first one, all of them are greatly interesting, but the one in 2018 is summarizing in a certain sense and achieving more than all the others, I think. So what he offers in 2010 is a quantifier-free, disjunction-free, and apartness-free intuitionistic axiomatization of the Euclidean geometry of ruler and compass constructions, which we call now ECG. So, quantifier-free, we heard already one time what this kind of thing is. Why wasn't I talking about this at that time? Because it contains relations. So, but it's stronger than those quantifier-free ones. First of all, it's intuitionistic. And second, there's no disjunction here. And he gets rid of the apartness story, which was there from the beginning of time. In other words, when Huygens started it. All construction operations are continuous in all variables on their domain of definition. So in other words, the thing you must do if something holds intuitionistically is to not have cases. You can't separate things. So remember those operations that we had when we did the constructing geometry in the classical sense. We said, well, if these intersect, then it gives you this point, else arbitrary. Well, that's very unintuitionistic. You can't do that. You have to do things that work uniformly for all cases. The aim of this paper is to show that Euclid is essentially constructive. That Euclid's 48 two-dimensional constructions and the proofs that they achieve their aims can be rather faithfully modeled inside ECG and very faithfully in its slight extension ECGD. This is a quotation from Michael Beeson. I forgot to put the end of the quotation. Yeah? So the multi-sorted language in which the axiom system is expressed contains variables for points, lines, and circles. There are three individual constants standing for three non-collinear points, relation symbols for point line and point circle incidence, for strict betweenness, and for equidistance. There are operation symbols for line-line intersections, line-circle intersections, circle-circle intersections, for point on line, for center of circle, for point on circle, for circle given center passing through given point, for circle with center, with given center and given radius, and for line determined by 2 points. So there's a lot of operations here, yeah? But remember, you want to do Euclid justice, to follow his reasoning and do it without quantifiers. The axioms are expressed in the logic of partial terms, in which whenever t is a term, you get this t down arrow, which is a formula that says that t is defined. There are 74 quantifier-free, disjunction-free axioms that axiomatize ECG. Most notable among them being several Markov principles. So the equivalence of the double negation with itself. So an axiom that says not B of ABC implies B of ABC. This sounds very unintuitionistic, but because it's applied only to atoms, you can see that it's not too bad. Yeah? So this is the only non-completely intuitionistic aspect of this story. ECG, again, if you interpret the symbols classically, you get a theory equivalent to Tarski's. Yeah? So plain Euclidean geometry over Euclidean ordered fields. If ECG proves in classical logic a statement A, then ECG with intuitionistic logic proves the double negation interpretation of A. So one where you replace exists with not for all not, and the disjunction with this. You don't need to replace everything with its double negation, every atom with its double negation, because we know already that the double negation implies the atom, so they're equivalent. So, ECG cannot prove this statement, for example. This is a statement about betweenness on a line. This is the one of the 4-point betweenness statements that, you know, if B is between A and D and C is between A and D, then A, D, C are in one of those orders. So if you have 2 points on a segment, then, you know, these points themselves are in some betweenness relation. It cannot prove that. So what Beeson does is he adds this as the 75th axiom, as well as another axiom implying that in the coordinate field that any non-zero element is positive or negative. This you need for some, you know, the Euclidean field in intuitionistic logic is a different animal. You get a theory, ECGD, which uses disjunction this time because you see it here. And it very faithfully reflects what Euclid did in his first book. Now, in 2015, there's another paper by Beeson. This time, it's no longer in this very rich language, but it is with quantifiers. The language is now exactly Tarski's language, betweenness and equidistance, B and delta. There's no apartness symbol in the language, nor can the standard properties of apartness, which can be defined, proved inside the theorem. Intuitionistic Tarski geometry, so this axiom system, if you add classical logic to it, is equivalent to Tarski's geometry, with or without line circle continuity, because there are two different setups. And Euclid's book 3 can be developed inside this axiom system. Now, in 2018, which is this culmination of this work, we get rid of Markov principles. You get an intuitionistic axiomatization again in Tarski's language, but this time without Markov principles. The Markov principles, this O should have been a P, are not only not among the axioms, but cannot be proved inside this. So you get rid of apartness, but you can't prove apartness. The secret to this achievement is, again, the many case-independent constructions, which are called uniform. So, for example, when you usually in the classical setting, you do different things when you drop a perpendicular or when you raise a perpendicular. In his system, you do the same thing. So this is not some kind of logical games. This is actual geometry has to come so you can prove stuff like this. So there's a whole new set of looking at things and constructing things in a different manner. Now I'm coming to the Steiner-Lehmus theorem and my tiny contribution to this, because, well, you could say, okay, what if I don't care about intuitionism at all? Then everything I've said so far is irrelevant because you don't care about intuitionism at all. Here is an example of why it is good for even the people who don't care at all about intuitionism. How it can solve something that originally had nothing to do with intuitionism. The Steiner-Lehmus theorem is a late addition to classical geometry. In fact, it could have been stated by Euclid as well. What does it say? It says that if you have a triangle where the two internal bisectors are congruent, then that triangle needs to be isosceles. The same thing if you do medians or altitudes is easy. Well, somewhat easy. No? For angle bisectors, it's not easy. Moreover, all the proofs that are known are indirect. What do they show? They show that if you assume that a triangle is not isosceles and the internal angle bisectors are congruent, then you get a contradiction. Or you prove that if one side is bigger than the other, then a certain internal bisector is bigger than the other. So all of this has some indirectness to it, and it's frustrating. You want to show that if these two are congruent, then those are congruent. So why do we introduce all this greater than and smaller than and this, which then goes to some contrapositive to get you this thing? And this bothered already Sylvester. He said, my reader will now be prepared to see why it is that all the geometric demonstrations given of this theorem are indirect. I believe I may venture to say necessarily indirect. It is because the truth of the theorem depends on the necessary non-existence of real roots, of analytical equations expressing the conditions of the question. And I believe that it may be safely taken as an axiom in geometrical method that whenever this is the case, no other form of proof than that of the reductio ad absurdum is possible in the nature of things. If this principle is erroneous, it must admit of an easy refutation in particular instances. So, although Sylvester expressed the belief that all proofs have to be incorrect, he leaves a small chance there that perhaps it's not. I call this Sylvester's problem, right? I mean, is there a direct proof or is there not? Well, in fact, all the way to the 21st century, there were people who produced things about, well, why there can't be another. One famous case is John Conway, who had produced arguments for this. So here I'm gonna start attempting to do this in classical logic, to show that there, what am I trying to attempt to do? To show that there is a direct proof. Now, Sara Negri and Jan von Plato in 1998 showed that classical axiomatizations, if they are in quantifier-free axioms, they can be turned into derivation rules in sequent calculus. And I'm going to show how that works. You have only two axioms. The first axiom is P gamma implies delta P. The second axiom says from nonsense and gamma, you can get delta. Okay? So this is a logic-free thing. Notice there are no ends, ors, implies, but just this implies. If you want, you can use a different sign for it. Yeah? You just have commas and the atoms themselves. Okay? So, and what are the rules? So those are the axioms, those two that you've seen, and everything else is rules of inference. Some rules of inference are from the, let's say, logical part, or from equality. And the others are rules that you get from your axioms. The equality rules say that if you can get delta out of A is equal to A and gamma, then you can get it out of gamma itself. And the second one says this: if you can get from S is equal to T, and QS and QT and gamma, you can get delta, then you should be able to get out of S is equal to T and QS and gamma the same delta. Well, the QA is an atomic predicate and so on. Okay? Now, the Sculemized axioms for absolute geometry are turned into rules of derivation according to the following principle. Each axiom of this form becomes this. So, let's see. You can write your axioms as, you know, this and this and this implies that or that or that. Then your axioms become this. What do you have here? You put all the P's all the time in front, and then you put one of the Q's. Here's the first one, then you put the second one, then you put the last one. So these are the premises. The thing you see before the bar is the premises. Yeah? And then you can infer that out of just the P's and gamma, you can get delta. So which says that if you have all of these things, so if I have this and so on, since I know that this implies that one of this is true, if I know that one of this is true, then I know that out of just this, I can get the story. Okay, so in our case for absolute geometry, the axioms, you've seen them in the first lecture. You get stuff like this. This, and so on. You get all kinds of sequence, you know, like that, with something up and something down. Another sequence, another sequence, another sequence. Yeah? So Now, there is a generalized form of the Steiner-Lehmus theorem that says, if you, let me draw it. Drawing, okay. No, this. Okay. So suppose I have a triangle. And this is the internal angle bisector. And I take a point, an arbitrary point on this internal bisector, and join it to this and join it to that. If these two are congruent, so the big one, so I have A, B, C, let's say. And this is M and this is N. And this was an arbitrary point here, whatever, S. Huh? Then if I have that Cn is congruent to Bm, then AB is AC. So why is it more general? Because in the Steiner-Lehmus theorem, Cn and Bm had to be internal angle bisectors. Here, I just joined C and B with an arbitrary point on the internal bisector of the angle A. And it's still true. So obviously, when these are internal angle bisectors, sure, they meet the third one in a point. But the general one says it doesn't matter which that point is. Okay, so let's first this, then do a few tricks here. Now it works. Okay, so this is how the thing looks like. It doesn't matter the exact things. Just look at it and see that it says, you know, not this and a bunch of things implies that. What does this become when you turn it into a sequent? This is what becomes. So you get all of these ends here. This not stuff, you had to put it in the other place. Yeah. Every not thing here got on the other space. Yeah. And you got this thing. There should have been an M is equal to A as well, shouldn't there? Yeah, probably. Yeah. Because you have everything with not is on this side. Yeah? So you get this thing, this thing. Okay. Now, what does it mean for a proof to be direct? Now we have to go into the philosophy of it. So, in this sequent language, there are no negation symbols because there's no logic at all. No. So we have just connectives or quantifiers. So how do we decide whether something is direct or indirect? Indirectness is commonly understood by using either proving the contrapositive of the statement or else arriving at a contradiction from alternatives to that statement. Now, contrapositive makes no sense in our sequent calculus. Why? Because each proposition gets turned in an essentially unique manner in a rule of derivation. All you can do is change the order of those things. You know, where you put the commas, you can make it else as just one. So indirectness, given that you can't get indirectness by looking at negation or other things, it occurs from two things. Either this is used as an axiom, but you have a nonsense there, or else a rule of derivation with empty upper sequence is used, because an empty upper sequence amounts to the statement that the antecedent of the lower sequence is contradictory. Yeah? If you have something from nothing, it means that something, whatever is before the gamma implies delta, the two things, the three things, the seven things are nonsense. Now, in the case of the generalized Steiner-Lehmus theorem, an axiom of this form cannot appear in the derivation of GSL. given that in our rules can appear only in gamma, and gamma carries over from the upper sequence to the lower sequence. So this nonsense would have to be present in the antecedent of GSL, which the antecedent of GSL is here. There is no nonsense symbol. Okay, so it can't come from there. So, which means that since you know that, we know that it's true in absolute geometry with Hilbert-style derivation, and we know that there must exist a proof in the sequence calculus as well. So none of our rules of derivation has an empty upper sequence. I think you've seen this is the only reason I listed them. These were the rules. None of them had an empty upper sequence, right? They all had stuff in it, yeah? Ups. Yeah, okay, so there was none with nothing upstairs. Everything had stuff. Which means that there must exist a direct derivation of this GSL. Now you might say this doesn't convince us. Why? Because the whole sequent calculus story would say is suspicious. Why? A critique of this approach to directness would be one that says that the original Steiner-Lehmus theorem, the one with small GSL, had what? Had this non-thing, and then just one thing, D is equal to C. But instead of proving this, we got this capital GSL, which had the conclusion was a disjunction of 6 things. There were 6 things there, right? In the end. It wasn't just C is equal to D, it was also everything that was not before. And everything that was not before was, you know, the fact that A, B, C are not collinear. Those were 3 B's, a B of A, B, C, and B of C, B, A, and B of B, A, C. And then there was N is A and N is C. So there are 6 things there. So you would say, well, yeah, I understand that these things are equivalent, but while you did this transformation, didn't you kind of sweep under the rug classical logic with all of its stuff? How do I know that this is really direct? Because you haven't proved the same thing. So don't we enlarge the set of directly provable sentences unduly? Now, it turns out that if you slightly rephrase a little GSL, so the one with, you know, in classical logic, you just have to say that the triangle is really triangle. It's not something with very small angles, you know, things like that. Then it can be proved from Michael Beeson's intuitionistic axiom system for Euclidean geometry, the one that was published in 2008. Now, there's no shadow of a doubt that this is direct, because there, any kind of indirectness is invalid logically. You know, if you think that you've done it with, you know, the contrapositive is a totally different story. So Sylvester's problem is finally solved. Yes, there is a direct proof, and it is direct beyond the shadow of a doubt. Now this is, how did I show this? By using a very deep theorem in Michael Beeson's paper. So I didn't actually produce the proof, which is very intuitionistically unpleasant, because existence in intuitionism is being able to display the object. Whereas I said, there is an intuitionistic proof, but I don't know what it is. Now, I'm not the only one making these statements. It is said that Brouwer once said, being asked by a friend, you know, what is Heiting doing? He said, I don't know what he's doing, but he's doing something about formalizing intuitionistic logic. So I may be allowed to say the same thing then, if Brouwer was allowed to say this. Now, more recently, in December 2021, a PhD student in computer science in Cornell, Ariel Kellison, claims to have actually found the proof and has a preprint about this in arXiv. And this is not done from Michael Beeson's axiom system, but from other things. And you're not given actually the output. And this is stuff that, I mean, it's probably, there is a printout somewhere which is unreadable for anyone. I don't like these things. Michael Beeson does like them. He thinks that that's the real stuff. I think the real stuff is things that I can read, and I can't read that, so I don't think it's real. So these, though, may contain lots of lines, you know. I remember that Julien Narbou told me that he proved something. I mean, he has a paper on this. He tried to formalize all the proofs in Schwabhäuser, Schmielek-Tarski's book, Metamathematische Methoden in der Geometrie. And he says somewhere that the proof of Pambuccian's theorem from Tarski's axioms for Euclidean geometry, I believe, are something like 10,000 lines. So perhaps these things end up to be the same thing. I don't know much about these things. And with this, I end my talk today. Let's see how going with questions. Thanks.
Thanks, Victor. Okay, questions? You can also stop the sharing.
How did we make this thing? The sharing. Okay, yeah. That shows me more of the audience. Yeah. Sure.
Okay. Questions? I have just questions. It's regarding the apartness relation and the decidability property. If I remember, there was a paper by Van Dalen about this, if you have apartness as a relation, the system is undecidable, or it's it's just I don't remember the title of the paper, but my question is if you can elaborate more about the
That's a very
apartness and the decidability.
That's a very good question. I haven't read anything in that sense, and actually, let's see. The question could be asked also about this axiom system that is for real closed fields in the intuitionistic sense. When you take Tarski and intuitionize it, Tarski's is decidable, but is this decidable? I haven't read anything about that. I don't think so, because Tarski's decision method and all the others don't carry over. And I'm not sure how this is with, I haven't read the one with the decidability or non-decidability of the apartness one. But if I'm thinking now about all these axiom systems, I've not read anything about decidability. They're also not complete because they can't prove several things, right? So there is a marked difference between these. I mean, the aim in them is to show that you can do any kind of elementary geometry in it, but not necessarily that you can do it automatically.
Yeah.
So So yeah, I believe that these will be undecidable. Yeah.
As I remember a paper, don't remember if the author was Mandelkern or probably also Gabay, but it's just a.
Because I think that this apartness occurs in many other contexts. It's also intuitionistic algebra and many other things which have apartness relations. It's not just in geometry.
Yeah. Thanks.
No.
Questions?
Okay.
Okay. There are no more questions, so thanks again, Victor, for your lecture. And next lecture is next Wednesday. The title is Into the Dark Night, the partial action in the order geometry. And thank you, people in presence and at home, and see you next Wednesday. Thanks again.